Welcome. In this video, I will be estimating a population proportion by constructing confidence intervals. A point estimate, that is, a single value estimate for the unknown population proportion, is the value of the sample proportion p hat, which is defined by x over n, where x is the number of successes in a sample of size n. The remaining n minus x are considered failures. The sample proportion of failures 1 minus p hat is often denoted as q hat. Suppose a random sample of 500 adults responded to a yes or no question. If 42 responded yes, then the sample proportion is 42 over 500, which is 0.84. This 0.84 is a point estimate for the population proportion. It gives us an idea of what the population proportion might be. However, it does not tell us that 84% of the population will respond yes. To infer or generalize about the population, we construct a confidence interval. That is, a range of values that we expect to capture the population parameter p at some confidence level. The confidence level represents the proportion of times we expect to capture the population parameter with repeated sampling. The confidence interval for p is computed using this formula: the sample proportion plus or minus the margin of error. The margin of error is the z-critical value times the standard error of the sample proportion. The standard error is the estimated standard deviation of the distribution of sample proportions. That is, an estimation of how much on average we expect the sample proportion to differ from the true population proportion. This confidence interval is valid when the sample size is large enough for the minimum required number of successes and failures, which could be 5 or more depending on your discipline. The z-critical value is determined based on the required confidence level. Z-critical values for commonly used confidence intervals are shown here. However, most confidence intervals you see in reports are constructed at the 95% confidence level, unless otherwise stated. But let's construct intervals at these unconventional confidence levels, given n equals 500 and p hat equals 0.84. Here again is the confidence interval formula. Let's first calculate the standard error. Substituting the values gives 0.0164. This value is typically very small, so it is important not to round intermediate calculations. Now for the 85% confidence interval, the area in details is 1 minus 0.85, which equals 0.15. This 0.15 is called the significance level, represented by alpha. That is, alpha equals 1 minus the confidence level. The critical value is the z-value separating the confidence region from the tail area. The tail area is called the critical region. The area in each tail is alpha over 2, which is 0.15 over 2, or 0.075. From the less than z table, the closest area to 0.075 is 0.0749, which corresponds to a z-score of negative 1.44. So separating the left tail here, we have the z-critical value of negative 1.44 and positive 1.44 on the right here due to symmetry. So we say we have a z-critical value of 1.44. Now, plugging that into the formula, we have a margin of error of 0.0236, a lower limit of 0.816, and an upper limit of 0.864. To interpret that, we say we are 85% confident that the true population proportion lies between 0.816 and 0.864. What that confidence interval really means is that if we construct 85% confidence intervals like this one for many random samples from this same population, in the long run, we expect about 85% of those intervals to contain the true population proportion and about 15% not to contain it. This interval is just one of those many intervals. It could belong in the 85% or in the 15%. In essence, this interval may or may not contain the true population proportion. For a 94% confidence interval, alpha is 1 minus 0.94, which is 0.06, and alpha over 2 is 0.03. The closest area to 0.03 is 0.0301, which corresponds to a z-score of negative 1.88. So the 94% confidence z-critical value is 1.88. Plugging that into the formula, we have a margin of error of 0.0308, a lower limit of 0.809, and an upper limit of 0.871. And for the 97% confidence level, alpha is 0.03, the area in each tail is 0.015, which we find exactly in the table, and that corresponds to a z-critical value of 2.17. Plugging that into the formula provides a lower limit of 0.804 and an upper limit of 0.876. That is, we are 97% confident that the unknown population proportion lies between 80.4% and 87.6%. From the results, we see that as confidence level increases, the z-critical value increases, which increases the margin of error, and in turn makes the confidence interval wider. Conversely, decreasing the confidence level decreases the width of the confidence interval. Apart from the confidence level, the sample size also affects the width of the confidence interval. Since the sample size is in the denominator of the standard error formula, increasing the sample size will decrease the size of the standard error, which will in turn decrease the margin of error and consequently reduce the width of the confidence interval. This agrees with the logic that larger samples are expected to produce more precise estimation. So a sample of size 200 will produce a wider confidence interval than a sample of size 500, but narrower than a sample of size 100. And that's it for this video. Thanks for watching.